Welcome to the lectures on fundamentals of MIMO wireless communications. Currently we are looking at fundamentals of information theory, where we are doing a revision of the important definitions and terms which are useful finally in the expression of capacity for MIMO systems. The last expression that we have derived in the previous lecture is that of mutual information. So there is also a corresponding diagrammatic representation of mutual information through Venn diagrams or through the set diagram. If this we would call as h of x, if this is h of x and this is h of y, and this particular part, in that case basically this is I of x comma y. So if you look at I of x comma y, I of x comma y says it is hx plus hy minus hxy. So basically this together is h of xy, right? And you could also match with this result, that what we have is it is h of y minus of h of y given x. So h of y, this particular part is h of y, take away x, and this is h of x given y. So in that case all these match. So I of xy is equal to h of y minus h of y given x. I of xy is basically h of x minus h of x given y. This I am taking out, okay. And finally the last one is this h of x plus h of y minus this one. What will be left with, this gets added 2 times if I do h of x plus h of y, and then I take away the union of them, union in which this appears only 1. In hx it gets added 1, in hy this section gets added once. When I take out the union, I take out this part, I take out this part, I take out ones from this, once is left. So that is also given by this description. So this is also well described through this particular diagrammatic representation. Okay, so with this we move forward to define an important inequality known as the Jensen's or Jensen's inequality. This is a very important inequality which we will use in some of the proofs where we show the positivity of some of the important constraints, and from which also derive some of the important results. So with Jensen's inequality, we start by saying that a function f of x is said to be convex over an interval a b if for every x1 comma x2 which is element of a and b, and for a certain lambda which lies between 0 and 1, if we have f, this function f of lambda times x1 plus 1 minus lambda times x2 is less than or equal to lambda times f of x1 plus 1 minus lambda times f of x2. So what this is saying effectively is that if I have an interval between a and b, I take 2 points x1 and x2 in this. So lambda lying between 0 and 1, and lambda times x1 plus 1 minus lambda times x2 is something in between this, because if you take lambda equals to 0, you are getting x2. If you are taking lambda equals to 1, this term becomes 0, so it is basically x1. So any other value would be somewhere in between. So f of a value which somewhere in between is less than or equal to the value at that point. So if this is f of x, sorry, if this is the point a that I have given, I would draw this as the axis. This is x, f of x. So whatever is the value of fx here, and let's say fx has a value there. So I take these two values, and again if you see lambda and 1 minus lambda is basically taking the mean of it. So if let's say fx goes like this, so f of x lambda times x1 plus 1 minus lambda times x2 is somewhere here, right? That is, if this value is x, this is fx. So if this is x, so f of this x goes here, and f of x1 is here, f of x2 is here. So any lambda times fx1, when lambda is 0, this becomes the value of x2, right? When lambda is 0 at x2, it is fx2. When lambda is 1, this is x1, this is fx1, because this term goes to 0. And so lambda, anything between 0 and 1 would be any value between these 2 points. So basically it is saying that the function value of the function between a and b lies below the chord connecting these 2 points. So that function is a convex function. So that is what is described by this convex function, and a function is said to be strictly convex if equality holds and only if lambda is equal to 0 or lambda is equal to 1. That means the equality holds only at these 2 points. In that case, it would be said that the function is strictly convex, otherwise it is just a convex function. Again, this will be used in some of the important proofs, and in this domain of MIMO wireless communications, this is a very important understanding, an important function, important inequality that will be used often. So a function is concave, we could write function is concave if minus f is convex. It's just the reverse of it. Okay, so this is just a description of it. Some of the convex functions, example of convex functions could be x squared, e to the power of x, x log x. So if you look at e to the power of x, it goes like this, there is a chord. If you look at x squared, it goes like this, so there is, it lies below the chord, and so on and so forth. And a concave function, one of them is log x root over x for x greater than 0. So here you would see that the function of log x typically would be going like this. So the function lies above the chord in this case. So these are concave functions and these are convex functions, right? So these will again be used, and the result of this definition we could write that if f is convex and x is a random variable, you could write expected, look at this, this is the average value. So writing e of fx is greater than or equal to f of e of x. So we could write it in this form in a concise notation, and if it is strictly convex, we could write that the equality holds, and in that case x equals to e of x. That means for the case when x is constant, this would be definitely true if it is strictly convex. Okay, we move on forward, and we would like to look at this, if this d of p given q, would like to look at this particular thing given the Jensen's inequality. So let us say that p of x and q of x be two distributions when x is element of some set, right? So these will be two probability mass functions. We would like to prove that d of p from q is greater than or equal to 0, and with equality if p is equal to q, right? So with equality if and only if p of x is equal to q of x for all x, right? This is what we would like to see. So let, for this we define, let a be defined as x for which p of x is greater than 0, and is also defined as be the support set of p of x, right? In that case, we would begin by writing minus d p from q could be written as minus x element of a. For the proof, we would start it with a minus. You could have done it with a plus also, things would have been similar, but here would follow it this way: p of x log px by qx. This is as per definition. So we are taking over the support. Over the support means we are taking the case for which px is greater than 0. That means we are not taking the case px is equal to 0, right? So this is what we have written. So we could write this as x element of a, p of x. So now since we move the minus sign inside, we could write this as log q of x by p of x, right? So this is just minus sign moving in, that is this gets invert because this is raised to the power of minus 1. Now we would use this Jensen's inequality at this point. Yeah, we're going to use the Jensen's. Yeah, already we have it here. We already have it here. So this particular function, we could say, because log is a concave function, is less than or equal to log of sum of x element of the support set of a px times qx by px. Look at this, what we have done. Now for this, for convex functions, we have e of fx is greater than or equal to f of ex. Now what we have is e of fx. This is the e, this whole thing is basically the expectation operation of fx, right? So what we have is, for convex functions is greater than, but for concave function it is the reverse, it is the less than. So that is what we have over here. So log of e of x, log is the function comes over here. So this is the function, and expectation moves inside. So we have this. So here now it is straightforward, px cancels. So you could write this as equal to log of sum over x element of the support set of a times q of x. So over the support set of x, this term, that is sum over the probability mass function, is equal to 1, then only there is a probability mass function, and this has only non-zero values. So basically this is equal to log of 1, which is equal to 0. So now what we have, minus d p from q is less than or equal to 0. So basically we have minus d p from q is less than or equal to 0, or d of p relative entropy is greater than or equal to 0. This will again be used in some of the further definitions. So one of the things which you can easily see from this particular thing is that d is the relative entropy. Mutual information is relative entropy, is also defined in terms of relative entropy of the joint distribution with respect to the independent distributions, the marginal product of marginal distributions. So if the Schoolbeck-Legblad distance or relative entropy is non-negative, in that case mutual information is also non-negative. We have seen entropy is also non-negative. So if we would go by the definition of mutual information, that is hx minus h of y given x, so that is what we have, hx minus of h of x given y, sorry. So in that case, again some important interesting results would come out because of this particular result that we have been able to derive in this particular case. So we look forward, we could write them down here. First and foremost, because d p from q is greater than or equal to 0, therefore we could say that I of x y is also greater than or equal to 0, right? And we could also say that I of x and y, which is conditioned on z, should also be greater than or equal to 0. So these are some of the important results that we have from the previous definition. That means this particular definition that we have got. Okay. So with this description, whatever we have described till now is basically for discrete random variables. So as we have said that we have these discrete sources and we have this discrete channel like this binary symmetric channel and other cases. We would also have the waveform channels. So waveform channels are continuous. So when we talk about continuous channels, we cannot work with these discrete sources, so with these discrete random variables. So we would also need to define these entropy and relative entropy and everything for continuous random variables. So we move on to our definition for the appropriate entropy term when we have continuous random variables. Once we are done with these things, then we'll move on to look at the expression of capacity for discrete sources and discrete channel, and then we'll move on to the waveform channel, where all we'll be using the results as has been described in the previous lecture as well as in this particular lecture. Okay. So we move further, and we would like to define differential entropy. Right. So differential entropy is basically the entropy of a continuous random variable. Now you will see the difference when we look at a continuous random variable, and that's why we need to give a different term, and we will not use the term as entropy. We would use differential entropy. We would not go and explain the details of why it could be possibly called a differential entropy, but rather we would see the implications of a continuous random variable and why it should be handled carefully, and why at least a different name should be given. Okay. So we go ahead. So we are looking at the entropy of a continuous random variable. So this is also related to the differential entropy is also related to the shortest length of a random variable. So this is also similar to the entropy, but there are certain subtleties which are different, which doesn't make the entropy of a continuous random variable to be treated exactly as the same way as that of a discrete random variable. So move forward with this. So this also gives us the shortest description length, right. So this also gives us, and now we would say that suppose x is a random variable with cumulative distribution function f(x) defined as the probability that x is less than a particular x. If f(x) is continuous, then we would say the random variable is continuous. Okay, and we would say let f of x is equal to f prime of x. F prime of x is indicating the derivative, right, and when this exists, and if integral minus infinity to infinity f of x is equal to 1, we would call f of x as the probability density function, right, probability density function for x. So these are some of the things which are necessary, and we would call the set where f of x is greater than 0 is the support set of x. Now this is important, because we are not taking the case where f of x is equal to 0, because that is not the supported set. So supported set would mean that range of x where there is a non-zero probability of x occurring. Otherwise we would have a almost infinite range of values of x that we have to deal with. So with this we move forward and define the differential entropy h of x. So now we will use the term small h instead of capital H, which we had defined earlier, of the continuous random variable x as integrate over the support set. S indicates the support set. So you are not integrating over the entire range of f of x log of f x dx with a minus, right. So this defines the differential entropy. So for continuous random variable, instead of using the term entropy, we would be using the term differential entropy, and we'll be almost deriving the expressions as we have done for the discrete random variable. And here also, if you further see that this description is dependent on f, right. So since this is dependent on f, it is sometimes also represented as h of f. So because this will be defined over the support set of S, so that is very important. Now just to see one of the important implications, that when we take this as a continuous random variables, so suppose I take a uniform distribution. Suppose I take a uniform distribution, and for which we say that the random variable is distributed between 0 to a, and so its density is basically 1 by a. So if I have to calculate h of x would be minus, going by this description, it ranges from 0 to a, it's defined in the entire range, 1 upon a log of 1 by a dx. So this integral would lead to log of a. So whenever for a less than 1, what do we get? We get log of a less than 0. So that means what you are getting is h of x, which is the differential entropy, can be negative, whereas what we have seen for entropy of a discrete random variables, it is non-negative, it is 0 or greater than 0. But here what we are seeing is that it can be a negative value. So therefore we cannot give it the same name as entropy, because we have a different variable to deal with, that is a continuous random variable, and therefore we would usually call it differential entropy, right. Moving forward, again we have an important result which is also used further. So if we would take the normal distribution, so when we take the normal distribution, we let x be distributed as phi of x. This is a notation that x be distributed as phi of x, and for normal distribution it is well known, it is given as 1 by root 2 pi sigma squared, where sigma is the standard deviation of x, e to the power of minus x squared by 2 sigma squared. That means we are taking a zero mean. When we say normal distribution, we are taking a zero mean, and the description that we are giving is given by this particular expression. So if we have to calculate h of, so as we had said, we could use h of f. So since phi is denoting the normal distribution in this case, h of phi is basically minus phi ln phi. So we are taking ln for the sake of ease at this particular case. You could do it for log 2 also. So I'll just give you the log 2 result at the end of it. So this is equal to integral phi of x times, so if you take the natural logarithm of this, what you end up with is this term. So log of this plus log of this. Now log of this is basically minus half ln 2 pi sigma squared, right. And the other part, what you are left with is when you take the log of it, this goes out, so basically minus x squared upon 2 sigma squared. So this is what you are left with in this case. So a minus sign, a minus sign, a minus sign, so all minus signs go away, so you are left with a plus sign. And if you are taking this particular, if you are taking, okay, so here we have a d of x, right. So if we are taking this particular term, let's say this particular term, we have 1 by 2 sigma squared, integral phi x squared is basically e of x squared. So when this term is multiplied, this term is integrated, this particular term with this particular term. 2 sigma squared is below, phi x squared dx is basically E of x squared, because this is the probability density function, and what you have is the rest of the terms. So plus sign a half, this is a constant, ln 2 pi sigma squared, integral phi x dx is basically 1. So we have only this term. This you could write it as E of x squared is basically sigma squared. So this and this goes out, so you have half. So when you have half, from half you could write, instead of 1 I could write ln of E. So that means it is the same thing. Basically this goes out with this, 2 remains, plus half ln 2 pi sigma squared. So what you have there, that leads to half ln 2 pi E sigma squared in nats, right, because we have taken natural logarithm over here. And if you take in bits, so it would turn out to be h of phi in bits would turn out to be half log base 2 pi E sigma squared in bits. So for arriving at this, instead of taking ln over here, one has to take log base 2, and then you would arrive at this particular expression. So you can try this as exercise. So instead of taking, so basically h phi, when it is defined as minus, when it would be defined as minus integral phi log base 2 of phi. So through this you are going to get this particular expression there. So this is again a very important result which we will use later on, right. So in this particular lecture we would stop at this point where we have started our journey into the differential entropy descriptions of continuous random variables. We have to do something more in the future lectures, so when we finally come up to the expression of capacity, which we will be using in defining capacity of MIMO channels. Thank you.